Well, the name is Transformations About Novelty and Persistence in the History of Chemistry. And I hope that Eugene Schwartz is listening to this talk, because for 2 or 3 sessions of this meeting, he insists in the word transformation. The overview is 5 parts: introduction and main purpose, scientific revolutions. I will talk about instrumentarium, a word used by Rom Harre, practices and subdisciplines. The third point is classical, modern, new chemistry, chemical transformation, and the last one about the conclusions. The introduction and main purpose of the talk is, I want to remember this citation of Aaron I.D. Although the rise of chemistry as a modern science becomes evident in the events of the last half of the 18th century, the foundation of that science reach back into an even earlier period. So chemistry, as far as we know, for him, started at the last half of 18th century. So I will defend here that chemistry emerged as a science with robust and widespread practices in Europe in the middle of the 18th century. Since then, it has undergone 4 major transformations. In a previous work 2 years ago, I reported on the most adequate interpretation of the history of chemistry through hacking time emplacement revolutions instead of Kuhn-type replacement revolutions. In other words, the result of a specific rupture, often the result of the incorporation of new instruments. I am quite agree with Alok of the importance of instruments in the practice of science, and new practices corresponding to new subdisciplines, and there is continuity. Not everything is completely lost. Just to characterize the hacking type revolutions, this citation of Sweber, amalgamate pure and applied concerns, and they transform a wide range of scientific practices and are multidisciplinary, with new institutions being formed that epitomize the new directions. So are wider than hacking type revolutions, but most important are emplacement revolutions. Something remains of the past. So the incommensurability concept is not as sharp as at the beginning Kuhn defended. I've been talking for a while now of 5 revolutions based in instruments. The first revolution is that the instruments appear in the bottom of the slide, quite well known. The second, the Kali-apparat, the polarimeter, the spectrometer. The third is about the electron and the isotopes. The fourth about the instruments, the instrumental revolution that you just call it. And the fifth, it's about new instruments. The electron detector instrument, the flash photolysis instrument, and something like that. I wrote about this in the last year, but I changed my mind. And so, first of all, what scientific instrument revolutions must require 3 things at least. The first of them is instrumentarium. Rom Harre tells us that each laboratory has its characteristic instrumentarium, the actual equipment available for an experimenter, depending on the generosity of the budget, and the instrumentarium will consist not only of what is in the storeroom, but also what is to be found there, purchased in the catalogs of instrument makers. And the instrumentarium refers to equipment necessary to carry out experiments in a given space. It mainly consists of the instruments and apparatus found in a given place, be it a room or the solar system. Second, about the practices. Kim tells us that a sudden advancement in chemical practice is more often caused by a radical innovation in analytical method than by a new theory. And Klaus Rutenberg, the last year, chemical practices, it means the dialectical combination of synthesis and analysis and the characterization of substances are generally different from those of physics. Chemistry is different of physics. And it means that practices are a series of coordinated and shared activities, rules, reason, techniques, purposes, beliefs that are disciplined through the change of correct norms or procedures and that have a stable structure with the ability to reproduce itself through different learning processes. Some of the norms and procedures change slowly and some others quickly. In the history of philosophy of science, there here in the last 25 years has been a turn to practices. And finally, about subdisciplines, the last Kuhn say that first, the episodes that I once described as scientific revolutions are intimately associated with the ones I've here compared with speciation. The mode of practice permitted by the new concepts never covers all the field for which the erudite one took responsibility. So he changed his original idea of incommensurability, and now, sorry, it's here. At the end of his career, Kuhn recognizes a different meaning of incommensurability, indicating that the emergence of new subdisciplines within a discipline as a result of a scientific revolution and accepted by a new textbook separated scientific communities. So this is a change because new communities appear. So about classical, modern, or new chemistry, Ursula Klein asks herself, what kind of science is chemistry? The first answer to that was, one possible answer to this question is, chemistry is a science concerned with material substance and chemical transformation of substances. But also, chemistry never was a pure science. We must remember this since the beginning. It has related with a lot of traditions. John McAvoy say that about the chemical revolution. Other than the shared aim of explaining the property of inflammability in substantive terms, the various phlogiston theories that were promulgated during this time lack the stability and continuity in metaphysical and methodological presuppositions that is essential for the formation of research tradition. It means that there were different, different phlogiston theories, different phlogiston models. So in the traditional idea of the rise of chemistry, of the first revolution, against which phlogiston theory was classical modern new chemistry built? Because there were some of them. So I want to show you several very important things that happened after the second half of the 18th century. One is about chemical industry. The evolution of the chemical industry must be regarded as an important concomitant of the Industrial Revolution. The word Industrial Revolution was quite important in the history of science, but the Close wrote a book called The Chemical Revolution before Kuhn wrote its own book, that the revolution was industrial in a way. So our point, Clow and Clow, of departure is approximately between 1750, the time of which sheer mass of materials to be handled and forced to stop rolling at 1830. So the chemical manufacture during the same period presupposes, as Alloc said now, an intimate understanding of the nature of the technical process involved. They grow together. The chemical societies. In the standard history of the chemical society, now the Royal Chemical Society, which was founded in 1841, its author noted that an association of persons interested in the advancement of chemistry was nothing new. For in the preceding decades, various chemical societies, generally of a local character and in most cases short-lived, has been started. So chemical societies start, as I can show you, in Edinburgh in 1785, and in different places in Scotland, England, and the United States. The chemical journals. All these journals were private commercial ventures, owned and edited by a single chemist, who often exercised a great deal of influence on the chemistry of the day. Le Journal du Physique de Rosier, Chemisch's Journal du Furfren der Nature de Creel, and look at the dates, 1771, and I will finish with 98. So journals appear in England, Germany, and France. So the atmosphere in Europe allows the experimental and theoretical atmosphere allows the rise of chemistry as a scientific discipline. First, with the experiments of Joseph Black in Scotland, with his first quantitative reaction. Later, with Henry Cavendish, with the isolation of inflammable air. Later on, Roebuck and Garbutt with the left chamber process. It means the industrial production of sulfuric acid was patented. Priestley and Scheele isolate oxygen. And Lavoisier discovered oxygen as an element and published the Elementary Treatise of Chemistry. Nicolas Leblanc patented the method for the industrial production of calcium carbonate. 320 tons per year. It's not a small quantity. Alexander Volta showed its electric battery to Napoleon himself. Nicholson and Carsley electrolytically decomposed water. Humphrey Davy isolated electrochemically potassium and sodium, and John Dalton published the new system of chemical philosophy, where he introduced the atomic model. And finally, Berzelius produces the largest table of atomic weights. So by the end of the 18th century, chemistry had become a fully recognizable profession. But modern chemistry is founded not on the precept of Lavoisier's antiphlogiston chemistry, but on John Dalton's atomic theory. Composition is the fundamental chemical property that the atomic theory symbolizes so powerful through its ubiquitous symbol and formulas, and Dalton's work constitute its first successful representation. Arabazis wrote a deeply discussion about theoretical entities, but atom is the entity of chemistry. Chemistry rise in Europe identified with the atom as its entity, and it remains as such until today. Atom is a hidden entity or epistemic object following as a chunk. So, about chemical transformation, transformation is simultaneously novelty and persistence. We transform what is already there, what we have, and there is always something that remains. Transformation are not absolutes. So instead of revolutions, Kuhn or Haken revolutions, replacement or emplacement revolutions, what happened in the history of chemistry were transformations. As I was convinced by several colleagues during these ISPC meetings in the last 5 years at least. So what is a chemical transformation? A radical interpretation of existing thought, recognized by contemporaries themselves, the resolution of a long-standing debate, the use of new instrumentarium, the opening of new subdisciplines, or the incorporation of new entities. It means that since the rise of chemistry, we have 4 chemical transformations. The first appears organic chemistry, and the entity was molecules or with its own isomers. And another name for this revolution is the Quiet Revolution or the Second Revolution. The second transformation, the subdisciplines were physical chemistry or chemical physics or nuclear chemistry as well. And the entities were electrons, nuclei, cores, isotopes, ions, and radicals. Other names was atomic number revolution or third revolution. The third chemical transformation was the subdisciplines were instrumental chemistry, quantum chemistry, or molecular biology. The entity was a spin, and the other names was instrumental revolution or fourth revolution. And the fourth transformation, the subdisciplines were organometallic chemistry, nanochemistry, supramolecular, green chemistry, or femtochemistry. The entities were the nanoparticles. Another names was organometallic regime, following Guillermo Restrepo ideas, or the fifth revolution. So hence, those are the other names: the Quiet Revolution, a book by Alan Rock, the Atomic Number Revolution by Brad Gray, Classical to Modern Chemistry, the Instrumental Revolution, and the exploration of chemical space and its 3 historical regimes. So the conclusion is, my conclusion, there was no such a chemical revolution. What happened less than 300 years ago was the emergence of an independent, robust, plural, scientific and industrial discipline that we call chemistry. And since its emergence and with the stabilization of its practices, chemistry has undergone 4 major transformations. Thanks and gracias. Thank you.
Tenés dos preguntas en el chat, de Elena y de Sukumar. Ahí tenés.
Elena creo que es una pregunta pendiente. I'm not sure.
Elena.
Yes, I think that the Elena question was a pending question of the other session.
The previous one. So the
previous
Sukumar question is the first. So
it was just a very short question. Like you mentioned pure science, but do you just mean something which has no direct application? Is that how you define a pure science as opposed to an applied science?
It's a science without instruments, a science without materials. That's a pure science for me.
Okay.
It means mathematics.
Okay.
Not physics.
Or philosophy.
That or philosophy. Physics require instruments as well.
Okay.
Okay, there's a question of Olympia first.
yes, my question is, you say, Jose Antonio, that the basic entity is atom for chemistry. I think that some people would not agree, because they think that the main entity is at least molecule, because you have to agree with substances. I mean, with something that are substances at the macroscopic level. Why do you use atom instead of molecule?
Because I agree that the work of Dalton, putting atom in the time of the Lavoisier work and all the work of that I already showed, was quite important, quite important. So, as you know, when we teach chemistry, we teach atoms. Even that, I agree that molecule is the center of chemistry. But atom was the beginning of chemistry. Perhaps is a better way to say that. Obviously, with the change that atom has suffered with all the time, yes. Eric.
Yes.
Yes. Well, they appear because was another name.
Well, if your point is that you're moving beyond talk of revolutions,
yes,
I find it strange that you're still talking about revolutions. In fact, you're talking about 5 revolutions.
No. I'm talking about 4 transformations. I used to talk about 5 revolutions. That's the point.
Oh, but then I misunderstood your almost last slide.
No, the last one was another name. Another old name was that.
I see.
So the first transformation is equivalent to the second revolution, the third to the fourth. That's the point. But were transformations, not revolutions.
Okay.
Okay.
Okay, I think that there are not any question more. We have 4 minutes. But
no,
well, I'm glad to hear of Jose Antonio's transformation in this respect.
Yeah, we were talking in the break of phase transformations.
Yeah.
Scientific theories being phase transformations, and you basically have come up with something like that.
As you know, Eric, we have been talking about this for a long time, and the word revolution is quite, in the original sense of Kuhn, is quite sharp, quite strong, and does not allow to recognize the very mild, slow changes that appear in the laboratory, for example, in the practices. in the practices.
Yeah, I agree with you.
Yes.
I just have a minor, it might be a very minor question. In the last slide, I think it was last slide, you had in the fifth revolution, you had the only entities were nanoparticles,
Yes.
but you also mentioned the green transformation or biomass transformations. So are biofuels and bioplastics not new entities that are being made in chemistry?
It's quite a point. I don't know if it's possible a biofuel can be an entity. It's an entity in a way, but this is quite a difficult task.
Okay, good.
That's,
You know, I'm gonna get the words wrong, but the polymers that make up the new bioplastics.
yes, but it's certain entities in this sense are hidden entities, epistemic objects, are entities that you cannot see, are invisible. That's the point. All of them.
Jose, can I ask a quick question
Please.
or make a comment? I mean, revolution language comes from solar system observation. I like transformation because it comes from alchemy and chemistry. But what I liked about your talk was that you centered on the problem of incommensurability itself getting disrupted because you have new communities of scientific practice.
Yes.
That their internal problems of incommensurability are of a different kind.
Yes. Yes.
Right. So I really appreciated.
Yes.
I mean, I agree with Eric that somehow we have to displace the talk of revolutions because they are flat transformations, they are translocations, they're not real productions of new scientific communities. But thank you.
But it's easy to recognize that each of these 5 subdisciplines, each one has their own lexicon, as Kuhn himself said. So they share atom molecule, perhaps, but they talk about biofuels and about femtoseconds. They work in different worlds in a way.